Okay, so let us begin our discussion of linear regression. And if you remember, this is the credit card problem again. And in terms of linear regression, what this problem is asking us to do is to essentially come up with a dollar amount, which is like a real number, right? So that's what we said regression does. The predicted value that we are after is the credit line or the actual dollar amount. The only difference here from classification is that we are going to remove the sign that we had for the approve or deny, right? We will just like have the actual real numbers here. So this is the final hypothesis that I need, which is W transpose X, right? And D here is like the number of features that we have depending on whatever problem or whatever application we are looking at. Okay, so this is linear regression. This is how the problem is defined. Let's try to visualize it before we get into the details. Okay, so here is a pictorial representations. Of course, if you have just one feature and y is like the predicted value, then in this two-dimensional space, you can think of the final hypothesis, which is h of x, um, as a single, like a line, right? So a line with some intercept and slope. Similarly, if you have like two features, x1 and x2 here, right? And you have some predicted value y, what you're trying to, like what your hypothesis should, ideally speaking, do is that it should insert that hyperplane there and minimize the in-sample error. So what is this in-sample error? What we are trying to do is to minimize the sum squares of these values, like how much each of the points deviates from this optimal line. Essentially, that's what we're trying to do. And that's how the in-sample error will be defined in a regression problem. Whatever h of x of n for every n minus y n squared. So basically you're calculating the difference of the point at like the value of x at the line minus the given value of like whatever that is, for example, y1, y2, y3, and so on, and getting the average of that, right? So this is also known as the mean squared error. Now think about it, like what is that optimal point or the optimal line that I can fit in? Well, that optimal line is going to minimize the sum squared differences, right? And so that's why this is the mean squared error in this like two-dimensional space. This is like fitting, this is equal to fitting a line. In a three-dimensional space, this is, or a higher dimensional space, this is equal to fitting a hyperplane, right? And in general, because our discussion is going to be completely general, although we are visualizing it in a certain dimensional space, like one, like two or three, but in general, we are talking about a d-dimensional space, right? So we are what our goal is to kind of go and minimize this in-sample error to get our final hypotheses, right? So let us begin actually doing that. So let us start with that. Um, Okay, so what we're going to do is we're going to derive the algorithm that minimizes the in-sample error for regression, right? Basically, we're trying to get the weights that minimize E in, right? So basically my h of x is going to have some weights, right? And how do I get those weights? So let us begin with that. Okay, let me quickly draw that small picture here for our own reference. And again, as I said, the discussion is going to eventually be like general. So this is how mostly the line fits. This is what it looks like. And let's say this is x and this is y. So our goal is to get this optimal h of x that has this w transpose x, right? This is our goal. And now we are going to define the in-sample error or the mean squared error in like as a function of w, because the weights are the only thing that will vary. I have the data, I have my y, I have my x, right? So the thing that's E in now is a function of is essentially w. So now I'm representing it for this problem, E in of w, which will now be defined as, let me just write that again here, which is the average of I is from 1 to n, right? And then whatever h xi for every I, obviously, minus yi squared. This is what this means in terms of the picture that we're looking at on the left. Okay, having said that, if you look at this particular value here, this can be replaced by what we want to achieve, right? So basically, this value here is going to be my in-sample prediction for point xi, right? So how can I express it? Like, what is the other way of expressing it? Let me write that down here. Another way of expressing that is W transpose X I, right? And then my yi whole squared. Okay, so now another way of representing this in sample prediction for point xi, and like usually in the language of statistics, is by using yi hat. So hat is like what is going to be my predicted or my calculated sort of value for that. And so this is essentially, this is nothing but w transpose xi. So basically in this equation, I can replace that 1 over n, I is from 1 to n, and this term here can be replaced by y hat. So this is going to be yi hat minus yi whole squared. So this is my mean squared error, or this is also known as standard regression error. So standard regression error. Okay, so what were we after? What was our goal? We are trying to get the predicted values, which is this, as close as possible to the actual values, which is this. So basically we are trying to minimize this mean squared error, right? Remember in classification, we were trying to bring these two terms very close to one another so that they have the exact same sign, right? We cared only about the sign, but now we have this like actual difference, actual value. So, and as I said, this discussion is going to be completely general. So that's why I'm moving on to something that's known as matrix notation. And let me move to another slide because I don't think we have space here. And that's because we're talking about like any general case in d-dimensional space. So that's why linear algebra comes to our rescue. And so we're going to utilize that and translate this E in of W in a more sort of a concise and compact form. So that's why I'm introducing some matrix notation. For example, the target vector or Y will be defined as this column vector of all these Y's that we have, right? So Y1, Y2, and so on up to Yn. Let's say I have endpoints, right? And then we have the prediction vector, which of course are the values that I'm going to calculate, and I'll always denote it by a hat, right? So then this should be a little bigger, y1 hat, y2 hat, and so on up to yn hat, right? Just to make things more precise. Now, one thing that remains is my data matrix. And if you remember, data is my x, right, as like a whole. And this is nothing but, if you remember, it is going to be an n times d plus 1 matrix. Why? Because d plus 1 had that augmented 1 because of the bias in the weights, right? And just to like quickly kind of understand why this was, like, or maybe review, we wouldn't have an intercept here if I don't include that bias and if I don't include the augmented value in my x. So just a reminder. And now this can be, if you remember, this was the convention is to always represent them like these x's as column vectors, like every row is a vector. And because it's a column vector, so the way we kind of represent x is something like this. And remember, this representation here, this matrix here, has that one included in defining every x. So that means this matrix with rows is like already including the augmented input vectors, right? So now the way we write it in linear algebra is that this is going to be x1 transpose and x2 transpose and so on, xn transpose, right? And so this is in the form of rows because my data will be like in the form of rows. Now, if we look at the mean squared error or E in that we calculated earlier, and I'm going to show you in a second, but I can replace a lot of values here with these new definitions, right? So here, this is the equation I'm talking about, right? So I can do some things here, right? And so simply replacing by these new definitions, that's all I'm doing here. Basically, if you remember from linear algebra, so any such quantity like I think it was yi hat minus yi squared or yi minus y hat, like whichever it was, any such quantity, right, can be written as a Euclidean norm squared, which is equal to like this squared difference essentially, right? So that's exactly what I'll be doing. So here I can write, it's a more compact way of writing this like norm squared way. And so what I'm doing is I'll write the norm of y hat minus y, because like the new definitions here, and this squared. Okay, so that's great because now I have a more compact way of expressing this And that's why we are using this linear algebra notation. So I have a more compact way of expressing my E in. And by the way, we are going to take it further. And for that, a quick review of certain things. And let me write it on another slide. So now, for any y hat, let's say y1 hat, right? This y1 hat would be my whatever weights I'll get, right? Transpose x1, correct? Now, this is nothing but an inner product, and we know that right from like day one, right? And so this can also be written as x1 transpose w, right? Everybody agrees because this is just the inner product, which essentially means that this is nothing but this row vector that we just talked about, transpose x1 times this like column that has like all the weights, right? Similar to that, I can write y2 hat equals w transpose x2 and x2 transpose w, which can be again written as, sorry, not this, the entire x2 transpose and then w, right? And so on. So basically I'll have some yn hat which can eventually be expressed as xn transpose and w, right? So if we look at it, this is nothing but my data, my x that I began with, right? So this is my data. All these vectors, right, are nothing but my data. So basically I can say that my y hat can be written as xw, right? I'm just like taking all of these and the weights, correct? So you can verify this yourself. So let me leave it as an exercise for you to go and please verify this. But of course, this is the intuition. This is how we can replace my y hat with xw. So because I have like a new sort of representation of y hat, I have my E in, or my regression, standard regression error, as a function of w equals 1 over n, and then the norm that we had minus my y squared, right? Okay, so that's all of that is great. Can we do something in addition to this? Can we do some kind of a simplification here? And by the way, this is like the linear algebraic definition for ensample error, right? So the linear algebra definition. Well, I would definitely like to kind of expand this and see if I can get something, because remember what our goal is? Our goal is to find the minimum value for this E in, and the more like detailed description of E in we have, the better it is. So one quick rule, or maybe let me write it on another slide, if you remember, is that if I have this squared, this is exactly equal to z transpose z. So I can apply the same rule here, right? So E in of w is going to be 1 over n x w minus y transpose, right? And xw minus y, right? And how about even like going further? So leave the 1 over n here. Let me just like multiply these. So this is going to be w transpose x transpose xw, right? Minus w transpose x transpose y. It looks okay to me. Yep. Minus y transpose xw plus y transpose y. Let me quickly give it a look. Yeah, looks good to me. Okay, so look at these two terms, and everything in here looks to me like it is a number, and so like the only difference is that the transposes are kind of reversed in each of the terms, but because they are numbers, we can combine them, right? So further like simplification leads us to x transpose x w minus 2 times w transpose x transpose y plus this stays the same. Okay, great. Now, again, a reminder, we want to minimize the error, right? So the only thing that is varying here are the weights. Rest of the other things like the x and the y's will be given to us. We'll have them, right? And so our knowledge of calculus tells us In order to get the weights for the minimum E in order to minimize this, one way is to get the derivative and set it to 0, right? That's a very known kind of way of getting the minimum values for weights. Now, in a 1 or a 2-dimensional max function, it's easier to get such a value, but in our case, it's a vector. And so what we have to do is we have to use rules from our vector calculus. So basically, the only slight update here is going to be that set the gradient of E in of W to 0 in order to get the minimum weight. So in order to get the optimal weights, we have to set this gradient equal to 0 and calculate for whatever W we get. And that W is going to be my final, like the weight vector that we need to minimize E in. So let me do this. Let's put a break here and continue this like calculation of the gradient and other discussion that follows with this entire algorithm in the next video. So I'll just stop here and then we'll move on in the next video.